I'm going to go straight away to X-ray diffraction. Basically, the main reason for us talking about it yesterday was the fact that what we're trying to understand is organization of materials in their solid state. And different types of organic materials in solid state can be divided as crystalline and amorphous. And we already know what they are and what the differences between them are. Crystalline materials have ordered structure, they have very well repeated pattern of organization, which we call here as a unit cell. And in this unit cell what we've got is a repeated pattern which we can build the whole structure of these interactions by just multiplying this in all sorts of dimensions, in all sorts of directions. Once we know how this is organized, we know how the whole crystal is built. And that's quite important for us, because we can, by coming back from the crystalline structure, we can actually even prove what molecules we've got. Why is this important for us? We already know, because pharmaceutical molecules are organic compounds, and they often organize themselves in different polymorphs. And polymorphism is not just a phenomenon which is typical of pharmaceuticals, it's typical to quite a lot of different materials. Polymorphism by definition says a molecule can organize itself in many different ways. Each molecule has alternatives, like we saw here in carbamazepine. This molecule, because of the nature of functional group it has this motif here, which is amide type group, and it has aromatic rings. Because of this presence of this functional group, they can pack themselves in three-dimensional space in many different ways, like it's proven now 4. We have 4 different polymorphs of carbamazepine. Each of them have a different pattern of intermolecular interactions. And the key message from yesterday was, in order to understand the solid state forms, we should be able to understand intermolecular interactions. And a very fanciful word for that is supramolecular interactions. Write it down, because it's something which you will meet when you start reading papers. People talk about this in this language these days for a reason. Supramolecular, as a word, means interactions beyond one molecule. What we're trying to construct in solid state, we're trying to construct chemistry in which we don't manipulate with chemical bonds. That's molecular interactions. That's what chemical reactions do. When you react one molecule with another and form another molecule, you change the bonds. You change the molecular structure. When we try to construct different solid forms, we are not changing any bonds here. These are the same molecules. Chemical bonds are not changing. What's changing is intermolecular bonds. So that's something which is an example of chemistry beyond the molecule. That's what it means, supramolecular. It's organization beyond a molecule. Okay? That's something which is important in understanding all sorts of structure. I mean, we can say the three-dimensional structure of protein. I'll come back to it in a second. When three-dimensional structure of proteins is a result of supramolecular interactions. Yes, Simon?
It's not a similar thing to intermolecular.
No, intermolecular.
Yeah.
Intermolecular interactions, well, yes and no, in a way. It's supramolecular goes beyond that. You can say that supramolecular chemistry, as part of chemistry, deals with intermolecular interactions. So that's interactions beyond the molecule, in which we don't change chemistry of the molecule. But it's based on intermolecular interactions.
Make sense? Like regions.
No, it's beyond what I mean by supramolecular is, if I wanted to do molecular chemistry, I would have to change chemical bonds. Let's say this NH2 group, I would want to add something to it and become NH, another CO group. That's molecular chemistry. I'm changing the molecule. In all these 4 materials, they're exactly the same molecule. They're just passed in different way. And the reason for that is, different molecules have different alternatives. If I added a water molecule in it or ethanol molecule in it, what I will create is hydrates or solvates. Again, different types of interactions will be present. And these molecules will pack themselves in three-dimensional space. Why is this important for us? If these molecules are crystalline, different polymorphs will have different melting points they will have different levels of strength of these interactions, hence they will have different solubilities. So if you put a molecule in the set and think you have a polymer like this, and I'm just bluffing my way through it because I have no idea what the melting points of this are, what solubility of these polymers are. Let's say you wanted to do this. Some of this molecule will be the most stable polymorphs, and some of these structures will be not that stable at all. Most likely, you will encounter the most stable polymorphs in all sorts of formulations. But often, the most stable polymorph will be the one which has the worst properties. You have very low solubility, hence very low bioavailability, and so on and so forth. And you might be interested in pushing less stable a polymorph, and let's say this one. I have no idea which one of them is more stable and less stable in this slide. So then you will have to say, okay, fine, now I want to create this polymer. How do I make it stable? Which is the area of research that will benefit me from this polymer? Because the last thing you want to create, okay, I'm making a formulation in which this is the polymorph I've got, but in reality, this will convert into this polymorph, which I would consider to be the most stable. Usually 1, 2, 3, 4 means order of stability. Polymorph 1 is polymorph 1 because it's the one which is the most abundant. Polymorph 2 and so on and so forth. Okay? How do we know about these structures? It's quite important. I will put some information on the blackboard about Nobel Prize winners, about X-ray diffraction and about NMR today, just for you to read over the weekend. You've done the course test, you've nothing else to do. And actually it's quite a rewarding week to do, actually talking about the series. So each of these polymorphs will have its own pattern of interactions, and we can distinguish the structures using X-ray diffraction. These powder X-ray diffraction pattern can be considered the fingerprints of structures. Let's just go back a little bit more again for the X-ray diffraction, what the principles of that are. So I'll just try to draw it on the board. The main principle of X-ray diffraction is, as a diffraction as a phenomenon, is a phenomenon when a ray of light meets an obstacle, it can have different outcomes of that encounter. If the obstacle is much bigger than the wavelength, there will be absolutely nothing that light will be able to do. It will be just reflected backwards. It's like this. It goes back to us. You don't see. I've seen the beam which is coming back from that. If the obstacle is much smaller than the ray of light, the wavelengths of the light which I'm using, it will just go through it. There's absolutely no problem. Diffraction is a set of phenomena which happens when the obstacle is of a similar size as the wavelengths of light which I project on top. And you've all seen oil sparges, you've all seen grids, you've all been in science museum and seen how diffraction can work. You can create all sorts of images with different lights and so on and so forth. Similar thing happens here. It's just what we need to use to observe diffractions in crystal is something which we call X-rays. X-rays, you know what they are already from radiopharmacy. Their wavelength of X-rays is of the same level as the distance between crystalline planes. Okay? All the crystalline structures can be constructed as a combination of those crystalline planes. We can imagine these planes are running through the crystal. In reality, and those who want to be confused, just listen now. Those who don't want to be confused, don't listen now. There are no planes in the crystals. This is all a fiction. What we have in the crystal is periodic arrangements of electron density. Electron density in crystals are looking like these planes. But obviously there is no physical planes. I didn't put molecules in grids like you are sitting in grids. That's not the case at all. But reality of that is this model works. So what we observe as a crystal is a combination of planes. And what I've selected to you here is just two planes. Every crystalline material has many of them, and they all run through a crystal. So what's happening here, I'm now trying to project a beam of X-rays on these crystalline planes. And let's just see what can happen in the case of X-ray beams. So, as we know already, what I have here is a beam. It goes like this. That is a wavelength, isn't it? Because that is now repeated to here, and repeated to here, and it goes so on and so on. That wavelength comes also from here to here. It's exactly the same. Make sense? Now, what I'm trying to do now is I'm trying to get to a situation I project the second beam here. And the beam I'm doing, the second one, I'll try to do it exactly the same. Okay? Pretty much the same thing, yeah? So what we've done here now is, those are two beams which we've got. In order for those beams not to cancel each other, they have to be in this state. Because if I had a beam now, and I put a third beam like that, and let's just say this way, it goes extreme way, it goes this way. Yep, that's a third beam. It has exactly the same wavelengths. That's the same wavelength, isn't it? But if I now add this beam to this beam, my result of this will be nothing. And eventually, if I have any sort of displacement of this, these beams will cancel each other out. So the only thing which I can see, the beams have to come out of the crystal exactly the same way. They cannot come out of the crystal this way. They have to come out of the crystal for them to come out and be observed. They have to come out like this beam A and beam B. That gives us nothing. And anything remotely related to even something like, let me just try another beam here, like this. This also gives me nothing, because eventually they will all cancel out. Okay? That's the nature of this phenomenon which we're observing here. This beam has to be exactly the same way. And we call these beams in phase. They have the same intensity, they have the same frequency, but now they have the same phase. The phase means they're matching in intensity exactly where they are. So, in order for them to come through this beam, what needs to happen now? What we also see in this particular figure, the beam, this is the beam A on top, and this is the beam B. The beam B has to go a longer distance. Make sense? It has to go through the plane 1 and has to come back. So it actually goes a longer distance than this beam on top. Make sense? So, what I need to have in the end, the difference of the path of these beams should accommodate the integer number of the wavelengths. The difference of pathways, and that's this. That's a difference of pathways. If you look at this, this is exactly the same from here to here. And this is exactly the same from here to here. This beam, until this point, they're exactly the same length. And this beam is exactly the same length from this point. Okay? So the difference between those is this plus that. This plus that. So this plus that have to be proportionate to the number of wavelengths. And in that case, I'll get this. And I will not cancel them. Make sense? Oops. All the other stuff is sort of geometry. We know what theta is. That can be derived from this angle straight away from D. If you know your trigonometry, you will know how it goes. this small beam is d multiplied by sine of theta. So that particular thing have to go to this. And that's the Bragman's law, which these people devised based on this very, very simplistic version of a crystal. Combination of planes running through space. What's the consequence of that is? In a crystal, I have several hundreds of different planes. Each of these planes have their own distance. So for each of these distances, I can find an angle at which I will be able to observe diffraction phenomena. So if I pass through a crystal at different angles, eventually I will encounter every possibility of crystalline planes. So that's what I'm doing here. I'm now passing through the crystal. This is my X-ray diffraction source. It goes to the material here. It passes through it, and then I'm collecting the pattern, what's gone out. So eventually, by changing the position, this can rotate. I change this angle at which this beam goes to the crystal, so I will encounter all possible planes inside this crystal. And that's what I measured here. What I've measured here is a pattern in which on the bottom part I have the degrees of angles, which means different crystalline plane, and that gives me all the structures. Make sense? So try to think about it in this way. What I'm trying to do, I'm deciphering the structure of the crystal based on the structure, on the combination of this crystalline plane which runs through it. And depending how these molecules are arranged, that's something which is called symmetry. We can actually find out exactly where these molecules are. It's a very powerful tool and has been used now for many, many years. When Rosalind Franklin was doing her DNA structure, to get a DNA structure from X-ray diffraction took her a year or something like that from the data. What she was doing in a year can now be done in an hour. But without her doing it in a year, we would not be able to do it in an hour. Because we have now computer power, we have now better instruments, we have much, much better X-ray diffraction sources, which can actually collect the data in much, much quicker rate. We can go to much smaller particles and so on and so forth. But the principle of that, what she was doing, is exactly the same what I'm talking to you about now. And that's why I want you to be knowing this from the point of view of fundamental science. And crystallography was one of the most important discoveries of the last century. That the fact that we can probe the structures of molecules helped us to understand a lot of things. And it's not just related to pharmaceutical materials. If you want to create a receptor binding target, what do you do in this case? You're trying to put a molecule inside the protein and you're trying to get a crystal structure, how they're binding to each other. Without this, you can't do that. So pay some more attention on this, and it will be quite rewarding if you actually invest some time reading about it. Okay, let's just go where we left yesterday. What I did yesterday was we talked about IR spectroscopy, and I've asked you about this. This was an example of the conversation which we had, why IR spectroscopy can be very much useful for understanding the structure. And I'm not talking here about structure of molecular structure. I'm talking here about how do we infer information about particle sizes or surface groups versus the bulk groups. What I've asked you to do yesterday was to explain to me what happens in this particular experiment. What happens in this particular experiment, and I've told you what I've done. I've taken two different batches of particles of cellulose, and in those two different batches of particles of cellulose, what I've done, I have exposed them to D2O. One batch was exactly intact batch. It's a batch which I received probably from a manufacturer, and another batch was a batch which we ground to much smaller particle size. And what I've done after that, I've exposed them to a vapor of D2O. So the question which I wanted you to think about was, what is the origin of all these lines? Why are these lines here, and what do they are? What do they represent? So let's just think about those two lines. This line and this line. What are they? Most likely. Any ideas? Anybody thought about it? Good. Go ahead.
The one like 3,400 is that the OHs.
It's a typical OH stretch. Very good. Great. These are OH stretches. We always see OH stretches in about 3,500. You already know it from organic chemistry. What is a line at 2,500? What is a line at 2,500? Any ideas? Yes. Again?
The ether groups, like the CO.
Might be, but probably not. It's not CO. Yes, Simon.
Alcohol.
Which ones? They're not here. It's only OHs we have, and we have all of these. This is not within the region of any CH2s or any CHs. So what is the peak at 2,500? Yes, tell me.
Do the tritium.
Say it again? Is deuteration, and why is that?
I don't know.
It's a good guess, just to try to develop it.
And I know that it deprotonates it or something like that.
So what your suggestion is, some of these OH groups, because I've now exposed this to D2O, can be now switched to deuteriums. What effect will it have on the frequency? What effect will this deuteration have on the frequency? And does it have to have any effect on frequency at all? Any ideas? Very good point as well. Because hydrogen and deuterium are two nucleus that have different weight, what we're observing here is a vibration of the bond, isn't it? So if we have OH and OD, the intensity or frequency of these vibrations will change. What I've done now, I've doubled the weight. If you imagine this as a oscillator on a string, now I increase this is oscillating like this, and suddenly this object is twice as heavy. So the frequency of that becomes affected. So what this is OD. This is OH, this is OD. What is this then? So we have now three lines. One of them we've discovered. One of them is OH at 3,500. Another one is OD at 2,500. What is the line at 3,000? Go ahead.
Would it just be a CH?
It's not within the same region. CHs usually will be sort of like 1,500, and they're not exchangeable, obviously. Any other ideas? There's also actually is an OH. This is an OH group as well. Yes, Simon.
The deprotonated.
But if you deprotonate oxygen, what are you going to be detecting? There will be no stretching of OH. If you don't have any protons on oxygen, you don't see the bond. This is still OH group. So what I'm saying now is I've got now three lines, and our assignment of that is this is OH, this is OH, this is OD. Well, how do I know it's OD as well? If I go back to this slide, that's a frequency. The frequency is related to the weight, isn't it? This is the mass of one atom, that's the mass of another atom, it's the sum of the masses. If I substitute proton for deuterium, I have the biggest effect of isotopic effect here. Because suddenly, instead of one here, I have two, and instead of one here, I have two. So this mass has become much bigger. So what we've done here, I've told you that there's 3 lines. 3,500 is OH, 3,000, around 3,000 is also OH, and 2,500 is OD. So now what you have to explain to me is a change of intensities. So that's kind of the whole point of this. Why do we see these lines this way, and why do the intensities change this way? Go ahead.
Between like the 3,500 and 2,500. Surely like the ground one, if he's going to get at the OH bonds and actually like form the bonds, just like the O bond. Whereas in like the crystalline, surely like there'll be like hydrogen bonding occurring between the crystalline structures, and so it can't really act as any reactants.
Almost there, but not quite. But let's just try to develop it. It's good thoughts. So what we're trying to do here, let's just think about the structure of materials, and that's what you're starting with. What you're starting with is we have a material which is intact and ground. And this is about accessibility. So you're almost there. If I have intact molecules, intact material, and that this line, yeah? What I've got here is I've exposed it to D2O. I still have a lot of OHs. but I still have some ODs. So what are these ODs? Where do they come from? They come from deuterated water. So everything which was on the surface of that material has been exchanged with deuterium. What about these things? What about these things? When I actually ground it now, the intensities of this line have gone much smaller. And the intensity of this line has gone much bigger. Why is that? Go ahead.
Could it be because the particle sizes have decreased, so that absorption?
Particle sizes have decreased, good.
So how much it's absorbing as the surface area is decreased? So it
No,
can't
the particle sizes have decreased. What does it mean the surface area
increase.
is increased? So what I now have, I have much more exposure of the surface OH groups to deuterium. So this is exchangeable now. They have more exchangeable groups. And there will be some part of the structure which is completely inaccessible at all. And that's probably SSP. So that's an illustration what I'd like you to be able to do. I'll give you some data for the workshop, and that will be on the blackboard by the end of today or tomorrow. And that will give some real spectra. And that I will be asking you what happened to that material based on the observation on the graphs. It will be slightly different to what you expect to see, but it will be interesting experience just to try to understand how we actually view these materials. So this is about IR spectroscopy. So IR spectroscopy is a good technique. It's very simple to do. Everybody has an IR spectrometer. The only problem with IR spectroscopy is, even when we have the very simple examples of molecules, the spectra are incredibly messy. You have a lot of stretches, and to select stretches and vibrations which are related to crystalline structure rather than to molecular bonds is very difficult. So anything we can do about eliminating some of this will be quite useful. So the next type of vibrational spectroscopy is called the Raman spectroscopy, and I'm not going to go through main details of that. It's quite an important tool, especially when you go to pharmaceutical industry these days, because it also allows you to understand how molecules are assembled themselves in three-dimensional space. The Raman effect is very similar. It sort of comes from the area of vibrational spectroscopy, but it has a very different selection rule. What we have in IR spectroscopy, in order to observe a line, we need to be able to see the change of dipole moment. Dipole moments have to change during the vibration to be able to be seen in the IR spectrum. In Raman spectroscopy, that's not a selection rule. In Raman spectroscopy, what we're trying to do, we're trying to understand there is a quantity which is called polarizability. Polarizability is a quantity which is related to electron density. And every molecule which has a lot of electrons, especially in pi clouds, and that's aromatic compound, they have a tendency of being able to be dislodged in whatever directions we want. We can polarize them quite easily. So if you have a molecule which is rich on electrons, and that's most likely aromatic compounds, you will be able to observe Raman vibrations. It is a spectroscopic tool which allows us to change this from detection phenomena. And what it also allows us to do, it allows us to eliminate quite a lot of lines from the spectrum, because now what you're relying upon is only the changes of these electron densities, polarizability. So in the end what you've got a possibility now to observe a spectrum, which is still a vibrational spectrum, which has much fewer lines. That makes it much more selective. And I'll show you a couple of examples of that. Most pharmaceutical ingredients, most APIs which we've got, they have aromatic groups. You've seen your list of pharmaceutical molecules. Most of them have aromatic rings. That's why I'm talking about Raman spectroscopy now, simply because that methodology allows you to detect some. Also, a lot of excipients, and by excipients we mean molecules or materials in which we're trying to put APIs to deliver. They don't have aromatic groups. So the signal of the excipient will be much smaller than the signal of your API. So your sensitivity of detection of API is much greater. The other problem which you often have with IR spectroscopy was water. If you have a lot of water, water will get you in the IR spectrum and it will be very messy. In Raman spectroscopy, water is a very poor scatterer. So water is not detectable pretty much. You will not see it. Which is a good thing because your spectrum is much cleaner. So what you will be observing will be lines which are corresponding to your API and pretty much nothing else. So whatever changes happen to your API, like in different crystalline structures, you will be able to detect much more easily. So let's just see what these are. This is a Raman spectra of amorphous and crystalline indometacin, and I'll talk about indometacin in the next hour quite a lot. Indometacin is a very interesting molecule, still one of those workhorses from the pharmaceutical industry. But if you look at these two spectra, they're different. This is a crystalline material, this is amorphous material. In what we see straight away, I can distinguish them. There are different lines present, and most importantly, I can quantify them. So Raman spectroscopy is often used. If I have a mixture of amorphous and crystalline material, I can actually say how much of each is present. And that's not an easy task at all. Remember, we try to do it with X-ray diffraction. That's not possible. Can we do it with a DSC by any chance? If you think about the question, can I distinguish how much of material do I have in a crystalline state and how much of material I have in an amorphous state using DSC? You know what DSC is? Go ahead.
Would there be a bigger energy change measured for the melting of the crystalline? Because the amorphous one has got the glass transition temperature.
I mean, basically, you will have two different thermal events. You will have a glass transition and a melting point. Well done. And depending on the intensity of different peaks, if you calibrate it properly, you will be able to tell how much of each is present, provided they are not masking each other. Because imagine you have an amorphous form, it has gone through the glass transition, and by the time it melts, it actually recrystallizes. So you will have a very spurious result in that case. Whatever was amorphous, when you heat it up, becomes crystalline. So you don't get this straight away. You have to be thinking straight away which way I'm going to go, which temperatures I'm going to start my experiment. But most importantly, DSC can distinguish between crystalline and amorphous material, and you can do quantification of those. So this is one example. Another example here is the different forms of the compound. Again, if you look at this spectra, compare it with IR spectra that I showed you before, they're much cleaner. The smaller number of lines you've got, the easier it is to understand what these lines belong to. And the easier it is to understand how these lines are affected by three-dimensional organization, because that's what we want to understand. So it is giving us very good sensitivity. We can detect aromatic molecules. We don't have a presence of water which interferes with us. It also has disadvantages, unfortunately. The way how this experiment is run, you will heat up the sample. When you heat up the sample, you can induce a lot of phase transitions and so on and so forth. So, in a summary, yes, it's an experiment in which we detect the changes in polarizability. It's ideal for APIs with aromatic groups. Water and small molecules do not interfere with those spectra, and we can also distinguish amorphous and crystalline forms.